Indices can take the form of negative numbers or fractions, and it's important to know what these mean. So if we had a number raised to the power of 1 over a, for example, we could also write this as being the same as the eighth root, if you like, of x. Now, if we extend that example, so if we had x raised to the b over a, where b over a is now a rational number or a fraction, we can rewrite this. So we'd obviously still have some kind of square root part, but we'd also need to take into account the effect of this b. So if we rewrite this as x to the 1 over a, we can see that to get this b on the top, we also need to raise this whole thing to the power of b. So we know this x to the 1 over a can be written as the eighth root of x. And then this whole thing is raised to the power of b, so we do this whole thing to the power of b. And you'll probably have realised that we can do this the other way as well. So we could have, instead of writing x to the 1 over a all raised to the power of b, we could write x to the b all raised to the power of 1 over a. And if you think about our multiplicative laws for indices, it would still work here. We'd still just multiply that b by the 1 over a to get b over a. But here we can see now the x to the power of b would be all rooted under that a, so we'd get the eighth root of x to the b. So these two are actually equivalent expressions, these things here. Now, if we had x to a negative indice, so x to the minus a, we know that's the same as writing x to the a all to the minus 1. And we know if we write something to the minus 1, it's the same as taking the reciprocal of that thing. So we could write it as 1 over x to the a. Finally, an important one to remember is if we have a number raised to the power of 0, and that is always equal to 1. So if we look at some examples then, let's start with an example where we have lots of different things on the numerator and the denominator. So we could have this, for example. So how would we go about solving this? Well, the first thing I'd do is I'd change this cube root of y into something that looks a bit nicer, so where we have y raised to an indices. So we know the cube root, or a root of any kind, is written as 1 over that number. So this would be y to the third, and then this whole thing raised to the power of 4. And we'd divide that by the square root of y, which we know is y to the half, because it's the square root. So now we can use our multiplicative law here for indices. So we could write this as y to the 4 over 3 divided by y to the half. At which point you should now see that we have two numbers with the same base being divided. So we now subtract the power of the one on the denominator from the one on the numerator. So we'd have y to the 4 over 3 minus a half, which should give you y to the 5 over 6. So moving on to another example, what if we had something like 8 over 27 to the power of minus 2/3? Now when we have some kind of more complex power like this, I like to split it up into things that are perhaps easier to solve. So we could rewrite this as perhaps 8 over 27 to the minus 1/3, and then that whole thing squared. Or even simpler than that, we could write it as 8 over 27 to the power of minus 1 to the power of 1/3 to the power of 2. And you'll see then that this thing becomes a whole lot easier, because we could just start with this middle bracket and work outwards, evaluating each of these powers every time. So this 8 over 27 to the power of minus 1, we know raising something to the power of minus 1 is just the reciprocal, so we'd have 27 over 8 now to the power of 1/3 all squared. And when we raise something to the power of 1/3, as we mentioned previously, that's the same as doing the cube root, and they've been nice to us here because they've given us cube numbers. So the cube root of 27 is 3, and the cube root of 8 is 2. So we'd be left with 3 over 2 all squared. And then we can just evaluate this squared, so we do the same to the numerator and the denominator because it's a fraction, and we'd get 9 over 4. To finish then, let's consider a bit of a harder example. So imagine we are given some information, perhaps that y is a third x to the 5, and they want you to express a quarter y to the half in terms of k x to the power of n. So what would we do here? Well, I'd start off by substituting in. So we want to substitute in our y into this expression to get it all in terms of x. So we could write a quarter y to the half is equal to a quarter and then a third x to the power of 5 all to the power of a half. So at this point we have some kind of higher order term in x raised to another power, and we know that when we have that we multiply the powers, but we do have to be a bit careful in this case because we have this a third pre-multiplying this x to the power of 5. So what we'd essentially get is a quarter multiplied by a third to the power of a half multiplied by x to the 5 to the power of a half. So a quarter and then a third to the power of a half, what's that? Well, that's actually 1 over the square root of 3, because we have to square root this entire thing because it's to the power of a half. And then this x5 to the half, as we said, that's one of our laws of indices, so we multiply the two powers together, so we'd get x to the 5 over 2. And then could we simplify this any further? Well, I guess we could rationalize this denominator because we currently have a square root there. So we could multiply everything through by root 3 over root 3 or something. And that would give us root 3 over 4 times 3 x to the 5 over 2, which would leave us with root 3 over 12 x to the 5 over 2.